This is part 3 of our lecture on chapter 1, starting with section 1.5, the stored program concept. So we're picking up where we left off with part 2, where we talked about basically how a program that we think about in pseudocode is stored in memory, and looking a little bit more about the sequence of memory reference. So what we're looking at here is a simple stored program machine. And really what this accurately describes is the operation of how computers worked up till about the 1970s. Today's computers have really departed from this model because they perform internal operations in parallel or even out of order rather than happening sequentially for performance reasons. But looking at our pseudocode, we can express the fundamental actions of a stored program machine. So in our stored program machine, we're pointing to the first instruction in memory. We have our repeat. We read the instruction at the memory location that we're pointed at, point to the next instruction, decode the instruction read from memory, execute, do that forever until we get to the end. But if we look at the pseudocode sequence that tells us that a memory reference, right, our memory read is required to fetch each instruction from memory, then we can expand the action execute for the instructions that we want to give. So we can see that an execution of an instruction on this type of machine requires at least 2 memory accesses. The first memory access is to read the instruction itself, and the second is either to read data from memory that is required by the current instruction or to put data in memory that has previously been created or modified by the CPU in an earlier instruction. So a stored program machine can operate basically what we say a 2-phase mode. We're either fetching or we're executing. So because it's necessary to access memory twice per instruction, the expression von Neumann bottleneck has been coined to indicate that one of the limiting factors of the stored program computer is the path between the CPU and the memory. And remember, we talked about how that's called a bus. Machines with different types of architecture have been devised to overcome this limitation, and we'll talk about those kind of in later chapters, but looking at this format of instructions that run on a stored program machine, we can kind of intuitively reason that the instruction format for a stored program machine can be expressed in different address forms, right? And we can look at the same instruction set in C, right? So we have our instruction pointer, a do loop instruction, setting that to our memory instruction pointer, which is where we read the instruction. We decode the instruction, we fetch the required data, execute the instruction, store the results, and we do this loop, right, while the instruction does not equal stop. So just a simple programmatic way of looking at this pseudocode example. And remember, we can think of that internal memory system like a list. And this figure here that we're looking at really illustrates the organization of that memory system. So the processor provides us with the memory address on the address bus, and a control signal selects the read and write operation, right? We talked about the read and write cycle. And we can kind of see that visualized here, the address bus giving us that address port, the data port giving us the data bus, and moving that data in and out through the system. All right, so as I mentioned in that earlier example, we looked at, how we can basically take that into address format, right? So let's back up for just a second. We can intuitively, reasonably understand that our instruction format for a stored program machine can be expressed in what we could term the 3 address format, right? Our operation, address 1, address 2, address 3, where operation specifies the action of the instruction, and the 3 addresses are the locations of the 3 operands in memory, right? The operands are the addresses of data and not the data itself, right? And when we first get into software development, right, we kind of learn this idea of by value and by reference. And by value, we always mean, like, if we have an integer and its value is 6, then we mean 6. But if we mean by reference, and what we're talking about with a memory address is literally the physical location of where that 6 would live. And so my analogy for by value and by reference, which relates to what we're talking about here, is if I give you a picture of my house, you don't know where I live, but you know what my house looks like. And in our example of by value versus by reference, if I damage that photo, like I catch it on fire, you didn't damage my house. You don't even know where it is. But if I give you the address of my house, not only do you know where it is, but you could come to it directly and modify it or damage it, and you're actually modifying the actual house. And so the operands are the addresses of data. We know where they are, but they're not the data itself, right? And we bold the font to indicate the address that is the destination of data. So we talked about P, Q, and R, our 3 operands instructions, where P, Q, and R are our symbolic names, our variable names for the addresses of the 3 memory locations. And in our 3 operand format, we could express this in that RTL notation. So remember, we talked about RTL, the way that we talk about and define operations that take place within a computer using this register transfer language. And so we have our operands and we have our values, which I believe in the next table we will see our values. Here we are. So 833, 123, and 710, right? We see that P, Q, and R. And then the binary memory addresses being 101, 110, and 111. And the computer instruction for add up here is the symbolic form of the actual instruction that would be stored in memory as a binary sequence of 1s and 0s. And remember, we name things with variables because memory addresses, in this case we're using binary numbers, are extremely difficult for humans to remember. They're very error prone. We could accidentally make a mistake with which one we're actually talking about. So we use those symbolic names because they're easier for us to remember. If you write P in a program, it's automatically translated to 101. The computer knows what you're talking about. It's easier for us to remember. So applying our hypothetical computer that has this instruction with our 3 addresses, and we're going to add P, Q, and R, which implements, right? Q and R equals P, right? So here, P, Q, and R are the symbolic locations. We know where they are. We can load those into memory. We can do the addition operation. And we can see here in the figure the flow of information for when an instruction is executed, and then we can demonstrate that structure of an instruction. Similarly, some computers use 2-address instructions. So in a 2-address format, we would have a situation where, in this case, address 2 is our source operand, and address 1 is both a source and a destination, right? So this is pretty similar to when we want to take a value, add something to it, and put it back into the exact same value. So we can see that location P and location Q added together, and then update location P. Right? This ultimately ends up destroying one of the operands, right? The source of operand P is overwritten by the result. Now, practical computers don't generally allow you to use 2 memory addresses in the same instruction. Most computers, right, if we actually think about what goes on under the hood, like the Pentium or the modern like Core i7 processors, they specify 1 address in memory and a second address as a register, right? That register is that single storage element in the computer. Usually they have names like R0, R1, and they're used to hold temporary data that we're using during calculations. So we'll have a lot more to say about registers later, but that really is how it works. We're only working with 2 operands, but that is the way it looks in our instruction set. So it really was the pressure to minimize instruction size that prevented first-generation microprocessors from implementing the 2-operand instruction. So typically they employed a single address instruction format, so that's in the form of an operation address. And because only one address is provided and at least two addresses are required, the processor has to use a second operand that doesn't require an explicit address. So we mentioned that goes in the register. And that second operand, when it comes from a register once, we call that the accumulator within the CPU. So a register behaves like a memory location. It's located within the CPU itself. And the term accumulator, which isn't really used a lot today because most microprocessors now have several on-chip registers, but it demonstrates the flow of information during the execution of a single operand operation. So let's look at this in kind of a visual format. So the result remains, right, that we can load the accumulator with the first operand, right? So we put this into our adder, we put that into the accumulator. The accumulator provides one or more of the operands that take part of the instruction and receives the results. And then we store the result in the third operand. And we can see how the accumulator in this case acts as the bottleneck because all of the data has to flow through it. So a major aspect of computer instruction sets is the addressing mode, or the way in which we specify the location of an operand. So the location of the operand may be given directly, like its location, or it could be given indirectly as a register, and we'll dig a little deeper into addressing as we go on. But when we're discussing computer architecture, sometimes we don't want to specify the actual addressing mode, so we just use a generic term like effective address. And so we might be able to say that register R1 is loaded with data from the effective address, and we use the effective address because it refers to all of the different ways of generating the address of an operand and lets us avoid specifying a specific address just for simplicity's sake. So before we move on to the next section, I just want to point out something, right? We've been talking a lot about basically computer categories. And computers have main memories that store large quantities of data and instructions, and we know now that we have temporary scratch pad type registers on the CPU. And first generation microprocessors had about 6 registers, whereas a typical modern microprocessor, it's going to have 16, 32, or 64 registers. We can categorize computers by the way in which their instructions act on data. So if an instruction can read source operands from memory, perform an operation on the data, and store the result in memory, the computer is called memory to memory. And these are computers like the Intel IA32, the 8086, the Pentium, the Core i7, right? Computers that you're probably already familiar with, you just didn't know it. And these can perform operations on 2 operands where one is in memory and one is in register. And the result that we get is written to either memory or a register. And these have memory to register or register to memory, depending on how you want to say it, architectures. And then we have computers that, such as the ARM and the MIPS, that perform operations only on the contents of registers and are called register to register computers. And these computers have a load instruction to put data in registers and a store instruction to transfer data from a register to memory. So really all of this to say, you know, we're talking about a lot of different types of computers that we can categorize based on the way that they operate and read their operands. And when we discuss issues in computer architecture, we're going to take examples from various different types of microprocessors, but for this particular course, we are going to focus initially on one type of processor, which is the ARM processor. Now, this is probably the processor in which you might be the least familiar because up until recently, consumer technology didn't necessarily include an ARM processor. But from an instructional standpoint for beginners, this is a great microprocessor to talk about. So I just wanted to get that out before we start talking about memory. So we talked about previously how memory systems are fabricated with the widest range of technologies found anywhere. And the fastest memory retrieves data at 10 to the negative 9 per second. The slowest memory can take over 100 seconds, which is like 1 to the 10th, 11 to the 11th power. I'm saying that wrong, but you get the point. So let me just put this into perspective. The ratio between my walking speed and the velocity of a missile is about, so let's say 1 over 10 to the 4th. Because of the growing disparity between processor and memory performance, designers have attempted to limit the effects of a relatively slow memory by fetching data from memory before it's needed in order to hide that waiting period, which we term as latency. So looking at this figure of our memory hierarchy, we can see this is a pretty classic diagram that shows the types of memory components in a computer, their speed, which is denoted as access time, and the typical quantities that you would find inside of a PC. You can also see here the ratios between speeds and memory sizes for each of the components. And our registers hold the processor's working data, which is that cache, as a stored or a fast store for frequently used data. DRAM provides the bulk of working storage, and then the hard disk archives programs and data. And remember, when we talk about hard disk, we're talking about flash memory, solid state drives, right? We're not going to differentiate right now. Hard disks are about 40 million times bigger than register storage and about 20 million times slower. So that maybe helps kind of put things into perspective. We've talked about how frequently used data is stored at the very high speed location of our cache memory. Right? And it has a much, much smaller access time than our main store. The overall performance of a computer might be as much influenced by its cache memory as its architecture of the processor itself, because it is so crucial that cache memory be quick. But cache memory is a pretty complex topic because of the fine details of its implementation of basically what makes it so fast. Cache memory basically contains a copy of frequently used data from the main store, like a little scratch pad, and sits on the computer's address and data buses and basically eavesdrops on transactions between the CPU and memory. And that is essentially why we can access things so quickly out of that register. So when that cache memory notices that an address from the CPU is the same as an address of a data element that it saved, it's like, ooh, I've got that. You don't need to go find it. And it hands the data to the computer and tells the memory, like, don't bother with this access. Like, I've got it. Right? So it seems like a funny analogy, but essentially that is exactly how it works. So the address book, right, that we have in memory, it's effective, right? We can think of all of the different addresses, kind of like a phone book of all the people that you might phone regularly. And then you have like that favorites list of people that you talk to on a very regular basis, and they might be like your favorites. So we can think of like memory as kind of operating in that type of analogy. Now we can compare that to the DRAM, which is the dynamic random access memory. And that's our main store that holds the programs as they're being executed. And it's immediate access memory, but composed of volatile semiconductor memory. And it's volatile because data is lost when power is removed. We probably realize that, right? Like we had something copied in our clipboard on the computer and we lost power, and when we brought the computer back up, the information in that clipboard is gone because it was being stored in DRAM. It wasn't being stored to the disk, which is what persists when the power is lost. You can't use it for long-term storage of programs because of the volatility. And when we look at immediate access of memory, we can start to talk about emerging memory technologies that talk about non-volatile memory that retains data in the absence of power, which is essentially what a solid state drive is. And really, memory is our vital importance to portable applications such as digital cameras, MP3 players, and our modern phones. So let's talk about the bus, right? The bus is the link, right? It links together two or more functional parts of a computer and allows the exchange of data. So our bus between the CPU and the graphics card, or we talked about the bus that links our CPU to memory, but buses also link computers to external peripherals. So if you have a printer connected to the computer, right, there's going to be a bus that sends information to that printer. And it's a vital element in a computer system. And we're going to talk much more about it later because it is so vital, but let's just talk about some key concepts. So looking at the figure here, right, it's just a bunch of circles and lines, but it illustrates the structure of a hypothetical system that you would have to have if you didn't have a bus. So we imagine that the blue circles are processing units that have to communicate with one another. And in this example, some units connect directly to one another, whereas other units have to communicate with several devices. But you can see these connections are complex and they're messy and they're redundant. And ultimately, this kind of design would be fairly slow. So if you modified this system by adding a new unit, you'd have to add new highways between all of the new devices and every unit in which it has to communicate. So updating would also be a cumbersome mechanism. So with the bus, we have a more streamlined way of communication. So this figure here demonstrates the advantage of using a common bus to connect all of the units together because it's one single data highway. Each unit has an interface between itself and the common data highway, and it's a much more linear type of communication. The problem with this arrangement that we see here is that only one device can communicate with another device at a time, right? It's like a single lane highway. And because there's only one information path, if two devices want to use the bus simultaneously, they have to fight for control, like a one-lane bridge. And we use the term arbitration to describe the process by which two or more devices that are competing for a resource basically get to talk it out, right? And so some systems have a special unit called an arbiter that selects which of the competing devices that are allowed to go ahead, kind of just choosing an order of precedence. Others have kind of a waiting queue system where someone has to wait their turn until the other unit is finished. Modern computers, of course, have more than one bus. There are buses within the chips themselves. There's buses between functional units. There's buses between buses. So we have a much more robust series of highways in order to make all of the data move as fast as we want it to move. And so looking at this next figure, we illustrate the structure of a system where we would have like two buses, right? For like a system that would be found in a more modern PC. So we have the processor in dark blue that communicates directly with bus A, which is a second bus. Bus B is connected to bus A via a bus interface unit, right? And this allows for more parallel operations. Two different devices can communicate on bus A, while a second pair of devices could communicate on bus B. And the buses can have entirely different characteristics and operating speeds, which is also something we could take into consideration. A computer could have a whole hierarchy and network of buses, and each could be different and optimized for its intended application. And the fastest buses on the computer are those that are going to communicate with high-speed memory or video devices. And really, when we start to think about the design and the construction of buses, right, they'd have to be optimized for pure speed. And we start to look at ways that we connect peripherals together, right? We know that there's different types of USB. You've probably heard of Thunderbolt, Firewire, right? These are all just different types of buses that connect our low-cost components and are designed for that speed as part of their functionality. So really, two recurring themes that we're going to talk about throughout the course that discuss memory interfaces are standards and protocols. A standard is an agreed upon way of designing a system, specifying it, or categorizing any other aspects, right? They're vital to everyday life. Standards are things like power sockets, right? Plugs must conform to agreed standards in order to allow us to take electrical equipment from one place to another. You might realize if you leave the country, they have different electrical standards, so maybe your things don't plug in. Or things about lighting or markings on airport runways or taxiways, right? Things that are standardized, so when a pilot departs Beijing and arrives in Boston, they can interpret the markings in the same way, right? Standards are important. And sometimes we've seen the effects of what happens when technology standards fight, which is, again, USB, different formats of USB, Apple having their own standard. Electric cars have this problem. Different types of charging ports have different types of standards, so different cars can't all use the same charging network. So, protocols are similar to standards but cover a narrower domain. A protocol governs the sequence of events that take place when two parties communicate. So when a computer sends data to memory, the write protocol defines the sequence of signals, the address, the write, the command, the data that's stored, together with the minimum and maximum duration of the signals. So protocols define by which we can use those standards. So you'll want to make sure and hold on to those terms. Some other terms that are important when we talk about buses, we often talk about bus width. The width of a bus is kind of like when we think about 2, 4, and 6 lane highways, right? So a 64-bit bus can carry 64 bits or 8 bytes of information at a time. We could also talk about smaller buses, right? A bus might have 50 information paths by which 32 of them can carry data. So when we talk about width, we're talking about the number of parallel data paths a bus has. Bandwidth of a bus is a measure at the rate at which information can be transported across. Going back to our highway analogy, this would be the speed limit, right? The bandwidth is expressed in either bytes per second or bits per second, increasing the width of a bus, while keeping the data rate constant increases the bandwidth. And then latency, I mentioned earlier, is the waiting period between a data transfer request and the actual data transmission. So typically a bus's latency includes the time taken to arbitrate for the bus before the communication is allowed to take place. So this is the end of chapter 1. In summary, in order to understand what's happening in the computer, we have to appreciate the difference between computer architecture and computer organization. Right? Architecture is concerned with the operation of the computer at the level of the assembly language programmer and represents kind of this idealized, abstract view, which is fine for software development. Computer organization is concerned with how the architecture is implemented by real gates and circuits. And although architecture and organization are unrelated in principle, we understand and know that they have to influence each other. So we've talked a lot about different types of computers, how it reads instruction from memory, executes them one by one, operates on that data. We've solved a simple problem and demonstrated the computer requires an effectively small variety of operations in order to solve any problem that can be solved. The stored program computer that we looked at, simple and elegant device. We also read through a short history of the computer, defined really the device that we call the computer, and really understanding it wasn't invented. A computer grew, as we know it, out of a series of developments. And each new development took ideas developed in the past and used more modern technology to implement them. Right? Computers in the 40s aren't computers by our standards, but they were computers. And so as we move forward with our course content, really understanding the why. How does it work? Why does it work that way? And how is it important to me as a software developer as I move forward in my career? That is the point. So I hope you have enjoyed chapter 1, and we will continue in the next section.